Start. Alright, hello again everyone and welcome again to another science video lesson. And in this video lesson that we will going to have, we will talk about physics. Now, what branch of physics? And that is kinematics. So kinematics is the branch of physics that studies motion of a particle. Alright, so in this branch, we will going to talk about the three entities, all right, that is said to be related to this to the motion of the object, and that is position, velocity, and acceleration. All right, so with that, we will not waste time and we will discuss that one on the presentation. Alright, so we are here to our presentation, and our topic today is position, velocity, and acceleration. So some people are very confused with regards to these three when they are talking about motion of the object. Now, in physics, alright, so in physics, we are dealing with, we were going to answer some question like, for example, you have the car on the picture. Where is it heading? Alright, where's the car heading? Alright, how fast is it going to that direction? Alright, so the third question is, what is the location of this car? Right? What is the location of this car? What is the location of the plane? Alright, where can we, where's the location of the snail or any object? Alright, so we will going to discuss this one and we will try to visualize them. Alright, we will try to visualize these three using vector quantities. Alright, so we will use some directional. Alright, so we will use some directions. Alright, in order for us to understand what is position, velocity, and acceleration. Alright, so before I start, so I would like to thank first the PHET simulation for providing me the simulation for this topic that we have right here. Alright, so let's get started. Alright, so let's start first from the first entity that we have right there, which is called the position. So what is the position? So position is the location of the object. Alright, so that's the definition of your position. So that is the location of the object. Okay, so and position can be distance or displacement. Alright, so when we say distance, we said it is said that distance is a scalar. So it tells us that distance is only a magnitude. Alright, it has only a magnitude. So whereas the displacement is a position that has direction. That is why displacement is a vector. Alright, in a daily language, distance and displacement are the same. Alright, but in physics, distance and displacement are completely different from each other. Alright, so before we go to this presentation, let's take a look first at the simulation on how the simulation defines position. Alright, so let's go to the simulation. Alright, so this is our simulation, and on this simulation, it shows us the vector arrow that you have right here on position, velocity, and acceleration. Alright, so you can download this simulation on PHET website. So later I will, the link is on the description of this video. And on this simulation, you can try some mazes here. Alright, so you can have the level 2, and one of the most difficult part of the race is this one. Alright, so the most difficult level. Alright, so we will not go through that, and we will just use this simulation to visualize what position, velocity, and acceleration looks like. Alright, so let's start first with position. Okay, so alright, so as you can see, if the alright, so if the arrow or if the position arrow, alright, doesn't come out here, alright, so what happens to the red ball? So the red ball is stationary. So if there is no arrow, the ball is stationary. But, alright, if the arrow is shorter, then therefore the ball travel from point A to point B in a shorter distance. Alright, so shorter distance. And if the position arrow is larger and longer, alright, if the position arrow is longer, therefore it signifies that the ball traveled from point A to point B at a farther distance. So, let's go back again. So, no arrow means stationary. Short arrow means shorter distance. And longer arrow is farther distance. And as you can see, the arrow direction is the same as the direction of the ball above. Okay, so meaning to say, if we are going to the right, so this is my right, okay, if we are going to the right, the ball is also going to the right. All right, so that's the position vector. All right, so that's the displacement. If the ball is going to the right, then the position vector is going to the right. Then if it's going to the left, going to the left. All right, so that is the position vector in this simulation. So let's go back to our presentation. All right, so in this, graph that we have right here, so we will use some Cartesian plane. So in order to visualize what is a position all about, so if it is a distance, we have certain points in your Cartesian plane that we can use as a distance. For example, what is the distance of point A? All right, so what is the distance of point A? So we can say that the distance of point A is 6, then 6, 7, 8. All right, so 6, 8. So that is the coordinate. All right, this is the coordinate of point A, 6, 8. Then what is the direction? All right, so let's have a direction. So okay, so we can have the direction. All right, so we can have the direction as northeast. All right, so the direction where the point A is located is northeast. All right, so that is now a displacement. Now, if you put an angle on it, for example, let's have I think this is 45. Alright, so let's put an angle on it. So 45 degrees northeast. So you complete now your description of your displacement. So the point A is located at 45 degrees northeast, 6, 8. Alright, so that is the distance. Alright, next one. We have another one, the point B. So point B is located at, so point B is located at -5. Right, so it means it is on the left side. Then -5, then 2. Something like that. Alright, so that is the distance. Alright, then the direction is, we have northwest. So let's have a hypothetical angle here. So we can say that this is 15 degrees. Alright, so 15 degrees northwest is the location of your point B. Alright, so let's have the point C. So the point C is 4, 4. Alright, so for -4, so it tells us this is the distance and the direction of this point C is southeast. Alright, southeast. So let's put some angle here. For example, we can have 35 degrees here. So the location of point C is 35 degrees southeast. Alright, so that is displacement and distance. Okay. Now, in measuring distance, we use an SI unit. Alright, and the SI unit per distance is meter. Alright, so meter. It might be attached to a prefix called kilometer, centimeter, so on and so forth. But meter is an international unit for measuring distance. Other books are using English, like miles, yards, feet. Alright, something like that. Alright, so example, we have here the distance from the head of this insect down to its abdomen is 1 millimeter. The distance of this pool is 50 meters from start to finish. Alright, so something like that. Alright, next. Now, to further understand what is displacement and distance, I have here a situation, alright, that we can use to differentiate this displacement and distance. Alright, so let's start first with the two people here, and these two people are going to this building. Alright, they are going to this building, and alright, one of them, person A, alright, person A walked to this spot and down to this spot. Alright, good. Alright, going to the gate of this building. Alright, so this person A traveled 10 meters and 5 meters going to that building. While person B, alright, so while person B This is person B's path. He used the, okay, so he is excited to go to that building, and he just went through the grass and other stuffs on this area. So he went through this path, and okay, you don't know, all right, what is the distance, all right, in this path. Okay, so where do you think, wait, now, what is the distance on this path? Is it much, is it shorter or longer than this path that we have right here? Now, in order to compute that one, we will use the Pythagorean theorem. So we have c squared is equal to a squared plus b squared. So we can compute this path by having 10 squared plus 5 squared. So it will likely to be 100 plus 25. So that will be 125. So square root of 125. So to compute for the c, so this is the c. So to compute for the c, that is 11.2, I think. Alright, so 11.2. So this is the distance of this path. So 11.2. So this is much shorter than the other path that you have right here. Alright, so basically, where's the displacement? Alright, on this picture. Alright, the displacement on this picture is the location, is the same location that these two person is going to. Alright, so this person use this path to go to that gate of that building, and this person A, use this path to go to the gate of that building. So person A traveled 15 meters, alright, and person B traveled 11.2 meters. Alright, so this is their distance. Alright, so this is their distance. So their distance are different because person A has two direction here, and person B has only one. Alright, so the distance is different in terms of their value, and the displacement is the same. Why? Why the same? Because they are going through one certain point, and that's the gate of this building. Alright, so that's the displacement and the distance. Right, so okay, let's talk about now velocity. So that is position. Alright, so let's talk about velocity. Now, velocity is defined as the change in position over time. Alright, so we will use again this Cartesian plane. Suppose this person, alright, so this person will travel through a 10-meter distance. So from this point, 5, and another 5 over here. So on this direction, so we have 10. Alright, so the person traveled through that distance and made it to that certain point in around 2 seconds. Okay, so he traveled the 10-meter distance in 2 seconds. So how much is its velocity? So we can have 10 meter divided by 2, so that will be 5 meters per second. So the person, this person over here, traveled 5 meters per second to cover 10-meter distance. Alright, so that is velocity. So over time, alright, so over time, the person's distance or person's position is changing. Alright, is changing over time. Alright, so that is what velocity is all about. Alright, so let's go back to our simulation and try to visualize velocity. Alright, so we're going back to our simulation, and let's click this velocity. So reset first, and let's click this velocity. So as you can see, alright, so let's take a look first on the description of the velocity. So if there is no arrow, alright, there's no arrow here, then therefore the object is stationary. Right, so the object is stationary, there's no arrow. Alright, but if the arrow is small, alright, if the arrow is small, so therefore the velocity of the object is slower. Alright, the velocity of the object is slow. Alright, because the arrow itself represent that the shorter arrow represents slow velocity or less. Alright, so next one. If the arrow is long and large, then the velocity of the object is faster. Alright, so okay, let's have another one. Okay, how about the direction? Alright, so the direction, alright, the direction of the arrow, alright, follows the direction of the object. Alright, if the arrow is going to the right, then the object must be going to the right as well. Okay, so if the arrow is going to the right and it is in longer format, alright, for example, velocity, if it is longer format and going to the right, the object must be going to the right as well. Now, if it is going to the left, it is said to be going to the left. It is going down, then going up, then also. Then what is very important here is that the arrow, the shorter the arrow, the slower the velocity. The longer the arrow, the faster the velocity. So that's how you describe velocity using vector arrow that you have right here. Alright, so let's go back to the presentation. Okay, so that is velocity and how to, what are the units? Alright, so what are the units of velocity? Alright, so the units of velocity, it depends on the distance and time. Alright, so we have miles per hour in some cars. In jets, we have kilometers per hour. Then in snails, we have meters or centimeters per second. And on falling objects, we might use meters per second or kilometers per hour. It depends. Alright, so these are some common units of velocity or speed. Yeah. Alright, so the question here is, what is the difference between speed and velocity? So, in daily language, speed and velocity are the same. Alright, in daily language. But in physics, speed and velocity are completely different. Alright, so when we are talking about speed, we are talking about the magnitude. Alright, the magnitude of that speed. So, how to compute that magnitude? By a distance over time. Alright, the velocity is a vector quantity, so this is a scalar quantity. So speed is a scalar quantity. It contains only magnitude. Whereas the velocity, alright, so this velocity over here is a vector quantity. Alright, so this is a vector quantity and it includes the direction. So it has magnitude, alright, just like the speed. And it has a direction. So for example, an object is going 10 meters per second. So this is a speed. Alright? 10 meters per second. But if you put something like this, the object is going 10 meters per second to the left. Right? So there's a direction, there's a magnitude, then therefore that is velocity. Okay? So that is the difference between speed and velocity. So let's put it into an application. For example, okay, so you and your friends are playing hide and seek. Alright, so we have your friends here. Okay, something like that. Okay, so number 1, number 2, number 3, number 4, number 5. Alright, so you are here. Alright, so you are playing hide and seek. Now, what is the difference between speed and velocity? Now, when you start playing hide and seek, these people around you, these 5 people around you will run away from you. Alright, so will run away from you. So, it might depend. Alright, it might depend. But hypothetically, guys, probably, alright, we can say that these 5 people around you has the same speed. Alright? But in reality, it depends. Alright? It depends. It has the same speed. For example, all of them runs around 3 meters per second. Alright? All of them. Okay, again, in reality, it depends. Okay. Now, what is velocity? Now, the velocity here is the... Alright, so do you think velocity and speed of these people are the same? Alright, so if you said no, yes, if you said no, you are correct. Why? It's because these 5 people will have different directions where they going. Alright, so therefore, although they have the same speed, these people have the same speed, but they have different direction. That is why their velocities are different. Alright, so is that clear, guys? So I will repeat. Alright, so the people that you have right here may have the same speed, but they have different velocity because they travel at different directions. Alright, so that is the difference between speed and velocity. Alright, so how to compute speed and velocity? How to compute speed or velocity? Velocity is defined as letter V. Alright, so we can use S if it is speed. Alright, so distance traveled divided by the amount of time it took that object to travel that certain distance. or simply vector v. Alright, so let's put it. Okay, so vector v is equal to distance over time. Alright, so this is the basic equation in kinematics. Now, from this equation, it will give rise to other equations in more advanced topics in physics. Example, like projectile motion, alright, so momentum, something like that, impulse, so something like that. So this thing, or this is the basic, alright, of all formulas in physics. So velocity is equal to distance or displacement over time. Okay, so now this displacement or distance is in meters and time is in seconds. So therefore, the unit of velocity is meters per second as a SI unit for velocity. Alright. Now, if I travel 100 km in 1 hour, then what speed do I have? So we use the velocity is equal to distance over time. So in this case, you don't need to change the units. Alright, you don't need to change the unit. It will fall at the same time on the unit of velocity that we discussed earlier. So it is 100 kilometers per hour. Alright. Only if the question is asking you to convert into meters per second, that's the time that you will change the unit. Alright, next one. If I travel 1 meter in 1 second, then I have a speed of, so 1 divided by 1, so you will get 1 meters per second. So that's the speed of the object traveling at 1 meter in 1 second. So that's how you compute speed. So nothing is too fancy about that one. Alright, so speed is not constant all the time. Alright, so the speed is not constant all the time. Cars stop and go regularly, and some runners go uphill and downhill. So on this situation, speed can change, alright, at different points. So that is why there is what they call average speed or average velocity. Now, what is average velocity? This is the total distance that an object traveled, alright, over a period of certain time. Okay, so total distance travel took by an object over a certain period of time. So that is average velocity. Alright, so let's take a look at this problem. Alright, so it took me 1 hour to go 4 kilometers on the highway. Then it took me 2 hours to go 20 kilometers using the street. Alright, so first thing to do is find the total distance. Okay? Now, in order to find the total distance, so you add the two distances that is present on the problem. So we have 40 kilometers and 20 kilometers. So 40 plus 20, that will be 60. Alright? So that will be 60. So, okay, next one. The total time. Alright? So find the total time on this problem. So we have 1 hour, then 2 hours, then that will be 3 hours. Alright? So, do not attempt to compute them separately, guys. Do not attempt to compute them separately because, alright, for example, you just compute the speed here and then you just compute the speed there. Alright? So, it will likely to fall on different answer. Alright? So, now you have your total distance and your total time. You can now compute for the average speed. Alright, so what is the average speed here? So the average speed is 60 divided by 3. That will be 20 kilometers per hour. So this person took 20 has a 20 kilometer per hour speed, alright, to travel on those two streets that you have right there. Alright, so 20 kilometers per hour is his or her average speed. Okay. Next one. So I have, there's a question here. So I have traveled 25 kilometers in 10 minutes. How many meters have I traveled? Alright, so how many meters it is? Alright, so as you can see, the question is not asking for speed. The question is not asking for speed. So, only by converting this one into meters, will give you an idea that the answer will be 25,000 meters. Alright, so that is this sample question is all about. So, please be careful, guys. So, read first the question before you answer. Alright, so next one. I ran 1,000 meters in 3 minutes. Then I ran 1,000 meters uphill in 7 minutes. What is my average speed? Alright, so okay, so what will be the average speed of this person that we have right here? So we can compute this one. So total distance. Alright, so we can have 1,000 plus 1,000. Alright, so we can have 2,000 meters. Alright, so the total time. Alright, so the total time will be 3 minutes plus 7 minutes is equal to 10 minutes. Now, using the velocity formula, distance over time, you can have the answer of letter D. Alright, so your answer will be letter D. So that is 200 meters per minute. So that is your average velocity. Okay. Alright, so again, velocity is a directional speed. Alright, so the speed of the object and the direction of it is termed as velocity. Alright, so these are some examples. Okay, so let's go to graphical analysis of velocity and in this distance versus time graph. Alright, now typically guys, in order for you to solve the slope of this graph, alright, in order for you to solve this graph, in geometry you use the formula slope is equal to rise over run. Alright, so we use rise over run in this in order for us to solve the slope of the graph. Alright, now in our case, since this is physics, so we are asked to find out what is the speed of this aircraft using the graph. Alright, using the distance versus time graph that you have right here. So what is the velocity of this aircraft? Now, fortunately enough, that velocity is also similar to how we compute for the slope. Alright, so we are fortunate enough that they are the same. Alright, so let's do it. Alright, so in this case, we have, okay, rise over run. So rise over here, then we have run over there. Okay, so what do we have right here? So we have the run. Okay, so it will travel from 3 to 6. So how many hours is that? So we have 1, so we have 2, then we have 3. So the run will be 3 hours. Alright. Now, how about the rise? Alright, so how about the rise? So the rise will be, alright, so the rise will be 600. Alright, because it starts here. Alright, so going there. Right, so going there, so we have 1, right, so if the interval is 2, so we have 2, 4, 6, that will be 600. Alright, so 600. Okay, 3 hours and 600 kilometers. Alright. Okay, so just I have a typographical error here. This is hours and this is kilometers. So basically, following the formula of speed and velocity, distance over time or rise over run, that is 200 kilometers per hour. So the speed of the aircraft on this distance versus time graph is 200 kilometers per hour. Okay, so that's how you analyze the graph. Alright, that's how you analyze the graph of distance versus time in computing velocity. Alright, so how about in different slopes? How about if you have a different slope? So what are you going to do? Alright, so it is very simple. So you have, alright, so what do you have right here? So you do the rise over run thing, alright, to compute for the slope, and that's the time you can compute the speed. So example, the one that we have right here. Alright, so the speed here is increasing. Alright, so the speed here is increasing, and as well as this one, it is increasing. Alright, so this one, alright, so this one that you have right here is 0. Alright, 0, this is 0 velocity because, alright, if you will compute this one, alright, so we have run, which is 1 hour, then rise is 0. So rise over run, alright, rise over run, 0 divided by 1, that will be 0. Right, so that will be 0. So the velocity here is 0 meters per second. And meanwhile here, so we have, or kilometers per hour, rather. Alright, meanwhile here, we have 1 kilometer per hour. And also, if you have right here, we have 2 kilometers per hour. Alright, so that's how you compute your velocity at different slopes. There you go. Okay. So, next one. Okay, so this is the distance versus time graph, all right, of the position of this person during the race. What was the average speed for the entire race? All right. Now, okay, there are two ways in solving this problem. Number one, you can compute for the slope, all right, of each of the segment of this graph. All right, you can compute for the slope for each of the segment of this graph, or you can find the distance of each segment. Then add them all together, you get the total distance. Then find the total time. Alright, find the total time for each segment. Then add them all together, you find the total time. But if it is a graph, you can go directly. Alright, you can go directly from starting here. Right? This will be your run. And this will be your rise. Okay, you can go directly there. All right, so there are two ways of solving this one. Okay, so it will be, all right, so it will be 12 kilometers for the rise, and so for the hour will be 6 hours. All right, so the answer will be 2 kilometers per hour is the average speed of the person who did race using this graph that we have right here. Okay, so that is 2 kilometers per hour. Okay, next one. So basically, what does the slope of distance versus time graph shows? So none other than velocity or speed. All right, so please do remember that distance versus time graph usually shows the velocity or speed of the object. Okay, so next one. Now, I have a question here. Which of the 3 racers or 3 runners runs fastest? All right. Now, as you can see, they have the same. Distance. All right, but they have 3 different times. All right. So Leroy is 3 hours, and Jane is 4 hours. Then Bob is 6 hours. Alright, so which of them runs fastest? So the idea is the steeper the slope, the faster the velocity for that object. Alright, so and if you take a look at this one, right, Leroy finished the race in 3 hours. Jane finished the race at 4 hours. And Bob finished the race in 6 hours. So it will tell you that the smaller time, all right, it took an object to travel on a certain distance, the faster it is. So therefore, Leroy is the fastest runner on the graph. Okay? There you go. Alright, so let's go now to the next entity, the last entity. So we have acceleration. So what do you mean by acceleration? Alright, so what do you mean by acceleration? So acceleration means speeding up. Alright, or in other words, acceleration is the change in velocity over time. Okay, you can use that definition as well. So this is a change in velocity. Change in velocity over time. Alright, so acceleration is the one that dictates what will be the velocity of the object. Alright, so later we will use the simulation for that. Let's finish this one first. Alright, so acceleration is the rate at which velocity changes. Alright, over time. Alright, so you can have an increasing speed. Alright, okay, in acceleration. You can decrease the speed in acceleration. Alright, and you can also, acceleration tells us it can be a change in direction. Alright? It can be a change in direction if you are describing acceleration. Now, acceleration is always a vector quantity. It never be a scalar quantity. right? So it is not a scalar quantity. So meaning to say, the direction of acceleration, right? The direction of the acceleration depends, all right, depends on the direction of the object. Okay, so let's take a look at the simulation. All right, there you go. Let's we are back on this simulation. Okay. Now, on this simulation, we were going to use the acceleration in this situation. And we reset because our ball went somewhere else. Okay? Now, in acceleration, we can say that, okay, if there is no arrow, alright, there's no vector arrow for acceleration, therefore the object is at rest. Okay? Now, if the arrow is small, okay, therefore the acceleration is alright, so the acceleration of the object is less. Alright, so the okay, I repeat that one. Okay, if the acceleration of the object is small, like the one that I have right here, small arrow, then therefore the acceleration is small, but the object starts to speed up. So as you can see there, alright, so let us repeat again one more time. So even though there's a small acceleration, the velocity of the object, okay, speeds up, alright, okay, it speeds up depending on what the acceleration you have. Alright, so depending on what kind of acceleration do you have. So if the acceleration of the object is somehow larger, then expect that the object travels faster. Right? So that's the velocity of the object. Okay. So if the acceleration is longer, the one that I have right here, the acceleration or the velocity is faster. Alright. So, for example, we have a changing direction. Alright. So let's start first with increasing speed. There you go. That is increasing speed. Okay, decreasing speed. Right, so unfortunately, the ball went somewhere else. Alright, so let's start it one more time. Alright. Alright, so this is an increasing speed. Alright, so this is an increasing speed. Alright, so increasing speed, then reset again. How about decreasing speed? For example, you started this way, and alright, so it did not decrease. Okay, so let's try it one more time. Alright, so what is a decreasing speed? If the acceleration is, alright, going that way and you suddenly stops, you suddenly brake, then the acceleration vector changes its direction over here. Then therefore, it will change the speed of the object. Alright, so the object might change its or decrease its speed. Okay, another example or another attempt. Alright, so then okay. So as you can see, the object stopped and it goes back again. Okay, so that is decreasing. That is decreasing speed. Okay, so how about changing direction? Alright, so how do we do here in the simulation, the changing direction? So I have right here, it's going there. Okay, it's going down there. Then afterwards, it's going this way. Okay. Okay, let's repeat. Okay. So at start, it's going that way. Then after that, the direction of acceleration starts to go this way. Okay, so as you can see, in changing direction, you change also the direction of your vector arrow. Alright, so it affects the velocity as well. Alright, so it affects the velocity as well. So that is acceleration on this simulation. So let's go back to our presentation. Alright, so that is what acceleration is all about. So it's always a vector. Alright, so there are different types of acceleration. Number one is increasing speed. Alright, so if the car speeds up at green light, just like what you've seen on the a simulation a while ago. It starts from, it has certain acceleration, and over time, that acceleration or that speed will be accumulated, and the object will start speeding up. Alright? Then therefore the velocity is increasing. So, okay, so if you have an acceleration, like if the object starts at a low acceleration, eventually over time it will start to increase further, then the object will speed up, just like what you have seen a while ago. Alright, next one. Decreasing speed. Alright, so decreasing speed. So, an object that decreases in speed, for example, if you have seen a dog in front of you, then you slam the brake of your bike, alright, to stop. Okay? So, you are going fast, then you have seen a stoplight, then you stop, then that is decreasing speed. Alright? So, another one is changing direction. So if an object change in direction, for example, it goes to the left and then goes up, then goes down, then goes to the right, then the object is said to be in changing direction. So it might be that the velocity of the object is constant. Alright? It might likely that the speed of the object is constant. So that is these are the three types of acceleration that we will encounter later on this video lesson. Okay, let's start. How do we compute? Alright, how do we compute for acceleration? So how can the car be accelerating if its speed is constant, 65 kilometers per hour? Now, if the car is in constant speed, then therefore the car is changing direction. Alright? So the car is changing direction, therefore it is accelerating as well. Alright? It is accelerating. So it starts at 65 kilometers per hour, then at 2 seconds, so 65, at 2 seconds we have 130. Alright, so 130 in 2 seconds, then at 3 seconds, it will be 195. Alright, so 195 and then so on and then so forth. So, it is accelerating. Okay? So, the velocity, alright, so the velocity of the object increases. Alright, increases at constant speed. Okay. Alright, so if an object is moving in a straight line, so we can use this formula in order to compute for the acceleration. So acceleration is equal to final speed minus initial speed divided by time. Or we will get the units of meter per second squared. Or we can use this one. Alright, so in other terms, this is defined as meter per second per second. So what does it mean? Alright, so what does it mean? An object with an acceleration of 1 meter per second squared means that the object is increasing its speed at 1 meter per second, 1 meter per second per second. So 1 second, that is 1 meter per second. 2 seconds, so we have 2 meters per second. 3 seconds is 3 meters per second, then so on and then so forth. Alright, so that is the definition of your acceleration here. So final speed minus initial speed. So sometimes I usually write there v sub f minus v sub I. Alright, divided by time. Alright, so next one. Okay, there you go. Alright, so let's answer this question. A skydiver accelerates from 20 meters per second to 40 meters per second in 2 seconds. So what is the skydiver's average acceleration? So what is the average acceleration of this object? Alright, so let's analyze first. Okay, let's try to find out which one is the initial velocity. Now, usually initial velocity is the first velocity, but it depends upon the problem. Alright, so this is the first velocity that you will encounter in the problem. Okay, so that is 20 meters per second. So that is written here. Okay, next one. How about the final velocity? Okay, So how about the final velocity? So the final velocity will be 40 meters per second. Alright, so 40 meters per second because that's the second velocity that you have encountered in this problem that you have right here. Otherwise, you will have, if you have different problem, you just read it carefully before putting it where is the initial velocity and the final velocity. So we have 40 meters per second. Okay, so the time it takes is 2 seconds. So let's compute. So the formula that we were going to use is acceleration is equal to, okay, so v sub f minus v sub I divided by time. Okay, so this is the formula that we will going to use. So let's plug in all the values that you have right there. So we have 40 minus 20 divided by 2 seconds. So that will be 20 divided by 2. So that will be 10 meters per second squared. So that will be your acceleration. Okay. Okay, so the skydiver accelerates at 10 meters per second squared. Okay. So or we can have 10 meters per second. Alright, so meaning to say in 1 second, the velocity of the object is 10 meters per second. At 2 seconds, that will be now at 20 meters per second. At 3 seconds, we have 30 meters per second. Alright, so next, let's go to the next question. Alright, so for the next question, we have a bus accelerate from an initial speed of 12 meters per second at a constant rate of 1.2 meters per second squared. What is the final speed of the bus after 15 seconds? Alright, so what is the final speed of the bus? Okay, so let's compute. Okay, let's look at, okay, so we are fortunate enough. Right, so we are fortunate enough that the problem provides already the clue, which is what is the initial speed. So we have 12 meters per second. So that is our v sub I. So 12 meters per second. There we go. Alright, next one. At a constant rate of 1.2 meters per second squared. So this is an acceleration that you have right here. This is an acceleration. So we have acceleration is 1.2 meter per second squared. Alright, then the time is 15 seconds. So the question here is, what is the final speed of the bus in this problem? Okay, so in order to compute this one, we will use this formula. A is equal to v sub f minus v sub I over time. Alright, so just ignore this one. Alright, so okay. So in this case, we will need to transpose the formula. We will need to derive the formula because we don't have a v sub f, alright, given, and we have a given acceleration in the problem. So we do not have v sub f. So we will need to transpose this one. Alright, so I think we can have v sub I, alright, is equal to, alright, so v sub, rather v sub f. Alright, so v sub f is equal to v sub I plus acceleration times time. Alright, so this is the formula that we will going to use in this problem that you have right here. Alright, so let's plug in the values. So we have v sub f is equal to 12 plus 1.2 times 15. Alright, so let's do the math here. Alright, so let's do the math. So our final unit is meters per second because final speed is the one that we are looking for. So 1.2 times 15, so that is 18. 18 plus 12, that is 30. Alright, so the final speed of the bus is 30 meters per second. So that is our final velocity for this problem. So the bus is traveling 30 meters per second as its final speed. Okay, so let's go to the next problem. Okay, as a sports car driver traveling at 42.47 meters per second Alright, slams the brake and comes to rest in 4 seconds. Calculate the average acceleration of the car. Alright, so okay, let's analyze first and let's look for the given. Right. It is said that the driver is traveling at this speed. So since this is the first velocity that we have encountered, so therefore that will be your V sub I. So 42.47 meters per second. So there you go. Alright, so where is the final velocity if there is? Alright, so do you think there is a final velocity? Yes, there is. So even though there's no number, alright, but the problem describe it at rest. Alright, so when we mean at rest, the object is at 0 meters per second. So it's stationary. Alright? So it stops, something like that. So 0, automatically that will become 0 meters per second. Then the time it takes, that is 4 seconds. Alright, so in order for us to compute this one, we will use the formula again. Acceleration, final velocity, again, final velocity minus initial velocity divided by time. So let's plug in the values. So we have 0 minus 42.47 meters per second divided by 4. Okay, so there you go. As we all know, 0 minus 42 is negative. Alright, so 42.47 over 4, that is 10.62. Alright, or 10.6. So that will be 10.6 meters per second squared. Negative. Alright, so what is the negative sign all about? The negative sign in this answer tells us that the object is decelerating. This is the opposite of acceleration, deceleration. This is decelerating. So it means that the object is is going at rest. Alright, so it's going from traveling faster and it stops, something like that, or it starts to decrease its velocity over time. Alright, so decelerating. So a negative velocity or a negative acceleration, take note, is deceleration. Alright, so take note of that one. Negative acceleration is deceleration. Alright, so it tells us also that the car is slowing down. Alright, and also it tells us that the direction of acceleration is, alright, instead of going here, the object is now going to the opposite direction. Alright, so let me demonstrate it in the simulation. Okay, so here we are again to the simulation. Okay, so let me demonstrate here what is deceleration that we are talking about earlier. Alright, if the object is traveling, alright, then suddenly it stops. Alright, right, so suddenly it stops. So unfortunately, our object went somewhere else. Alright. So, okay. So if the object is traveling at greater acceleration, then it suddenly stops. Okay. So it went somewhere else. Okay. So, okay. If the object is traveling at if the object has greater speed and suddenly it stops, like the one that we have right here, so then it goes somewhere here. Alright, so as you can see, the object stopped. Alright, so it means that if the object is accelerating forward, alright, so if the object is accelerating forward, then suddenly it changed direction. Okay, so you cannot stop the object with higher velocity. So that is momentum. Okay, so you cannot stop object with a higher momentum. Okay, so if the object is traveling to a certain direction, then an opposite acceleration happens. Alright, so therefore the object is decelerating. So as you can see on the simulation, the object travels faster, then it starts to become slower and going back to its opposite direction. Alright, so that is the answer to this question. A negative acceleration is called deceleration. Alright, next one. Okay, so we have the graphical analysis for acceleration, just like what we did on the velocity, but this time we have velocity versus time. All right, so velocity versus time we are going to use here on this part. Okay, so all right, so in this kind of graph, so in the distance versus time, the slope or the rise over run is equal to the slope. That is velocity. Now, in this case, we have here velocity versus time. Okay, so if you want to compute the slope, so rise over run, so the answer will be on this, the answer for this one is acceleration. Alright, so in short, slope and acceleration is the same here on this graph. Alright, so the velocity is increasing with time. Alright, if the velocity is just, if the graph looks like this, then therefore the velocity is increasing over time. Okay, so if the graph looks like this, the velocity is increasing. Okay, if the line is straight, therefore the acceleration is constant. Okay, there is a constant acceleration. Okay, for example, what is the acceleration here? Okay, so we can have run, which is 1 second. Then the rise is 2. Right, so the rise is 2. So 2 meters per second. So 2 divided by 1, so that will be 2 meter per second squared. So therefore, all throughout this segment, the acceleration is constant. 2 meters per second, 2 meters per second. Alright, so that's how you use the slope of the line in computing for acceleration. Alright. Okay, so just like what we did earlier. Okay. Alright, so how about this one? Okay, so how about this one? So this time, this is distance versus time. Alright, so this is distance versus time. So what is, okay, so what will be the velocity here? Alright, so because this is distance over time, so the slope here should be velocity. So what will be the velocity here? Is it increasing or decreasing? So the thing here is, this is increasing. Alright, so increasing velocity, something like that. Okay, so if the velocity is increasing, so therefore its acceleration is also increasing. Alright, so this is an increasing acceleration that we have right here. This is an increasing acceleration. So it tells us that whenever we have a slope like this, it tells us that the velocity is increasing, and at the same time, alright, and at the same time, the acceleration also increasing. Okay, so next one. Okay, how about this one? Okay, so how is the velocity of the car changing? Is it speeding up, slowing down, or staying the same? Alright, now, if the slope is facing to the left or to the right, if the slope is facing to the right, then therefore, we can say that the object is decelerating. Alright, the object is decelerating. So from higher speed, it goes down to 0. So the object is slowing down. Alright, so what is the car acceleration? Okay, so what is the car's acceleration? So we can pick a slope here. For example, this one. What is the rise? The run, which is 1 second. Then the rise is 2 seconds. 2, right. So we have 2 meters per second. So the acceleration of the object is 2 meters per second. Alright? To the negative. Alright, so to the negative. So it is decelerating. Okay, so that is for this graph. Okay, so take note of that one. Okay, whenever the slope is going to the right, therefore we can safely say that is decelerating. Okay. Alright, so on this graph, which line represents an object that is accelerating? Alright, so which object? Alright, so is it the blue, the red, the black line, or the green line? Alright, so you can pause the video to analyze first the graph. Alright, and okay, try to find the answer. Alright, so the answer here is, alright, the black and red lines. Alright, so the black and red lines are are objects that are accelerating. So the black. So why? Why the black line? Because this is increasing speed. When you increase in speed, alright, so take note guys, so when you increase in speed, therefore your acceleration is, the object is accelerating. Alright, so the question here is, which object is accelerating? So the black lines definitely accelerates, but in positive. Alright, but in positive. But the red line, alright, so but the red line is somehow decelerating. Alright, even though it is decelerating, alright, so even though it is decelerating, it is also, alright, so it is also, alright, so the curve line on your slope, or the curved slope that you have right here, tells us that even though the object is slowing down, it is still accelerating, but in different direction. Alright, in different direction. So remember that the red is going less each second and it must be slowing down. Alright, so take note that one. And please remember that curved line means accelerating, flat line means constant velocity. Alright, so the blue line is constant, the red line is constant over here. Alright. So meaning to say they have one, alright, they have one set of speed all throughout a certain period of time. Alright, so let's take a look at this one. Alright, so what is the graph? Alright, so this is the graph of velocity versus time. Okay, so this is the graph for velocity versus time. Okay, what would be the distance versus time of this graph look like? Okay, now, if the graph is going this way, alright, so if the graph is going this way, so therefore it is an increasing velocity. Alright, or increasing, constant velocity rather. We have constant velocity. Alright, so what does the graph looks like if it is a distance versus time graph? Alright, so it will look like this. Alright, so it will look like this. Okay, so the object, alright, so the object starts to slow down. Alright, it starts to slow down as time passes by. Alright, so that is, alright, so that is your distance. So I forgot to change this one. This is distance versus time graph. Alright, so distance. Okay, so there you go. Okay, so basically that is for the acceleration. Alright, so before I finish this video, let's have a summary of everything that we have right here. Alright, and a comprehension check afterwards. Alright, okay, so remember that the slope of this displacement, is called velocity. Alright, so remember the slope in displacement versus time is called velocity. Alright, so let's take a look at this graph. So what does this graph mean? So a flat line displacement, the one that you have right here, it tells us that the object is stationary. Alright, so the object is at rest. Okay, so stationary. Okay, next one. How about this one? Okay, so if the displacement versus time graph looks like this, then therefore this is a constant velocity. Okay, so meaning to say it has one set of speed all throughout different time period. Alright, one set of speed. Alright, next one. How about this one? So what is the meaning of this? Alright, so what's the meaning of this graph? If it is curved line, like the one that you have right here, so this is increasing. Right, so it means that this is increasing velocity. Alright, so again, we have stationary, constant velocity, and increasing velocity. Alright, so let's go now to our velocity. Alright, so we have now velocity versus time graph. Alright, so I will just draw it right here. Alright, now, if the graph says, if the graph of velocity versus time is somehow like this, right? Okay, as we all know, the slope of velocity versus time graph is acceleration. Slope is equal to acceleration. Okay, so what does this one tells us about the acceleration of the object? So therefore, the acceleration of the object, if the velocity looks or v or velocity versus time graph looks like this, so therefore it has constant acceleration. Okay, so it has constant acceleration. Okay, so there you go. Next one. So how about if the graph is giving us this kind of data? Okay, so we have time. Okay, so what if this graph gives this kind of data? So it tells us that, all right, it tells us that this is increasing. All right, this is an increasing acceleration. Okay, so increasing acceleration. All right, so next one. What if the graph, all right, is curved? All right, so what if the graph is curved? Or rather, let me clarify this one. Yan, so let me clarify this one. Okay, let me clarify this one. So this is okay, so okay, so I think that is
If displacement at time velocity.
okay. So this is okay. So if you have a velocity versus time graph that looks like a straight line that you have right here, this is a uniform acceleration. Uniform acceleration. So meaning to say, okay, it tells us that okay, so uniform acceleration. Okay, so sorry for the all right, so sorry for the technicalities here. So let me repeat it one more time. Okay, so if you have all right, so if you have velocity over here, so if you have a velocity which is a straight line, all right, a straight line, but it is not a slope, all right. So the thing here, this is a uniform. Okay, so this is the uniform velocity, right? So meaning to say, all throughout the given time period, the velocity doesn't change. Alright, so the velocity doesn't change. Next one, if this one, alright, if you have a velocity versus time, okay, if you have a velocity versus time graph that looks like a slope or straight line slope, so this is a uniform acceleration. Okay, now when it is curved, so this is the velocity, this is the time. When it is curved, it tells us that the acceleration is increasing. Alright, we have increasing acceleration. Alright, so as you can see, the acceleration is increasing over time. Alright, so this is the velocity versus time graph. So don't forget, straight line means uniform velocity. Slope, straight slope means uniform acceleration, and the curve one is increasing acceleration. All right, so please do not forget that one. All right, so okay, so next one. All right, next one. We have here another graph which is acceleration versus time. All right, so what does this one means? All right, so a straight line, acceleration versus time. So a straight line means, all right, so a straight line means this is a constant, or this means that your acceleration is zero. Alright, so it tells you that this is a constant velocity. So you have zero acceleration, because if you have a constant velocity, for example, 4 meters per second, your initial, minus 4 meters per second, your final velocity, then your time is 2 seconds. Alright, so you will have an answer of 0. So this is a zero acceleration. Alright, so zero acceleration. So straight line. Next one. How about this one over here? Alright, so how about this one? So the straight line that you have right here means you have constant acceleration. Right, so constant acceleration. Okay? Alright, so this is constant. Next one. How about the curved line? Alright, so what does the curved line means? So the curved line means that it is the curved line means that your acceleration is increasing. So this is right. So this is increasing acceleration. Right. So those are the graphs. All right. So okay. So you need to remember how the graphs can be interpreted on this acceleration, velocity, and position. All right. Let's go now. How to visualize this position, velocity, and acceleration. So the ball is rolling over there. All right. So the ball is rolling, and let's put first its velocity. All right. So the velocity is, the position. All right. The vector for position for this ball is increasing towards that direction. All right. So it is increasing. Okay. Next one. How about the velocity? So the velocity is somehow decreasing. Alright, so it goes that way, but it is decreasing. Why? Because the ball stops. Alright, so as you can see here, the ball stops, then it goes that way and decreasing. Alright, next one. How about the acceleration? So the acceleration is going that way at constant speed, right? So at constant speed that you have, at constant, all right? So it goes that way, all right? Then once it stops, right? So it stops. The acceleration now at this point, starting to go on this direction. All right? So that is because the friction that acts on the ball, right? So the friction that acts on the ball, okay, enables it to stop. Okay, so that's how you visualize your position, velocity, and your acceleration. And finally, all right, you can pause. All right, so you can pause for this one if you want to if you want more time to answer this question. Okay, so what we're going to do here is to answer the following things at the bottom of the question. So in a car from rest, you begin accelerating in the forward direction. Alright, so forward. Okay. Now, once you hit the maximum, right? So once you hit the maximum, what do you have? Maximum speed, you decelerate to a stop. Alright, so just like what the car on the stoplight. Alright. So then you put your car in reverse and return to your starting point the same way you came. For each section, state whether each corresponding vector, which is displacement, velocity, and acceleration, points forward or backward, and its magnitude. If it is increasing, decreasing, or it stays the same. Alright, so let's find out, guys. So let's find out. So let's start first with initial acceleration. This is the time that you go your car from rest to moving forward. Alright, so let's start. Okay, let's take a look first at position. Alright, so position. It says here it's forward. So you are going forward. Then, what is the magnitude? Alright, increasing. Okay, because you are going forward. Alright, so that is increasing. Next, velocity. Alright, so velocity. What is the velocity of the object? So it is still forward. Alright, because you hit the maximum speed, so therefore that is increasing. Okay, there you go. Next one, how about acceleration? Right, so how about acceleration? So, where are you going? Forward. Okay, you're going forward and your acceleration, you hit, alright, so you hit the maximum speed. Alright, so you hit the maximum speed, so therefore, it is said to be increasing. Okay, so there you go. Okay, so in initial acceleration, right, so in initial acceleration, we have position forward, alright, velocity is forward increasing, and acceleration is forward increasing. Alright, so rather, okay, so I will change this one, so forgot to mention. Alright, so since your velocity is increasing, so therefore your acceleration is constant. Alright, so constant. So you have a certain set of acceleration. That is why your velocity is increasing. Alright. Next one. Okay. Next one. And the initial deceleration. So what is the car's initial deceleration? Alright, so we have first the position. Alright, so or displacement. Alright. So the car is going still forward. Alright, and is still increasing. Alright, so you just slow down and still going forward. Next one, we have velocity. Alright, so we have velocity. So the object is going forward, but it starts to decelerate. So it tells us that the velocity is decreasing. Alright, next one, acceleration. Acceleration, so you start to decelerate, you start going backward. Alright, you start going backward, but in constant magnitude, or it stays the same. Alright, so constant. Okay, next one. Okay, so that is for the initial deceleration. Alright, so let's go now to reverse acceleration. Alright, so position. Okay, in reverse acceleration, so still you are still moving forward. Alright, you're still moving forward because you suddenly reverse. Alright, so you're still moving forward, but that forward direction is decreasing. Alright, that forward direction is decreasing. You start going now backward. Alright, you start going backward. Okay, next one. How about the velocity? Alright, so the velocity now is backward. The velocity now is backward, and that is increasing because you accelerate. Alright, increasing. Then therefore, your acceleration is backward because you are going in reverse. So backward and constant. Okay, so that is backward constant. So that is letter C, reverse acceleration. So did you get it correctly? Alright, so that's good for you. Alright, so next one. So next one is the position for the reverse deceleration. Okay, so in reverse deceleration, so the object starts to slow down. Alright. Still going forward. Okay, because in the initial acceleration, this is present, or this is our answer to our initial acceleration. The object is going forward and it is increasing. Alright? So, as it goes backward, there's still some vector arrow that goes forward, but it starts to decrease. Right? So, decreasing. Alright, next one. So, as you reverse accelerate, the direction of the velocity is backward. The direction of the velocity is backward because you are going in reverse. Alright, so backward, but you are starting to slow down. So therefore, decreasing. Okay, so there you go. And finally, we have for the acceleration. Alright, so for the acceleration, so you are you are going in reverse direction that is treated as forward. Alright, so that is treated as forward, but alright, since you are decreasing, alright, so you are decreasing or you are slowing down, alright, in the process, so therefore that reverse deceleration is also constant. Okay, so there you go. Okay, so it doesn't increase unless your velocity is increasing. So therefore unless your velocity is increasing, so therefore your acceleration will be affected on that point. All right, so that is the comprehension check. So double check your answer here, guys. So please pardon me on this one. So okay, so I forgot that the object is increasing, so therefore it must be constant. Okay, so with that, okay, so that ends up our discussion regarding our video lesson about position, velocity, and acceleration. And with this, alright, so with this particular video lesson, you'll be able now to understand the three entities which is directly related to the motion of the object. Alright, so before we end up, okay, so if you gain knowledge about this video, just hit the like button on the bottom of this video. Alright, and if you want to be updated for more videos like this in the future, just hit subscribe and the notification bell on this video. Now, if you have question about what you have seen on the video, or if you have suggestion about what topic I might going to make a video in the future, just comment it. Just put your comments in the comment section of this video. Alright, so that's it for today, guys. So let's see each other to the next video lesson. Alright, so peace out, guys.